Welcome to Week 6 Ensemble Learning. In this week, we will build from what we learnt last week on decision stumps and trees to instead now build highly powerful ensembles, techniques which remain highly popular and competitive with deep learning due to their strong balance between interpretability and generalizability. The learning objectives for this week are to seek that you gain a strong grasp on the intuition for using ensemble learning, understanding the difference between the most well-known types and being able to identify the key strengths of each of these. We will look at homogeneous and heterogeneous ensembles and sequential and parallel approaches, each of which approach the task of improving model accuracy and reducing overfitting in different ways. Of these different classes, we're going to specifically focus on homogeneous learning methods, specifically bagging, random forests, and boosting. Bagging and forests are very similar techniques based on common principles and are examples of parallel learners. Boosting, on the other hand, reflects a family of sequential learning methods. The idea is that you solidly understand what motivates each of these approaches and are able to link this to how they are implemented. We'll then have a go at implementing a bagging model from scratch by essentially training a large number of decision trees and combining their results together. This will use the decision tree implementation that we started last week, where there is a separate completed Python module in your Keep space containing all the code that you'll need, so don't worry if you didn't complete it last time. As always, we will look at implementing all methods in scikit-learn. And at the end, we will provide a high-level overview of the concepts behind heterogeneous ensembles. These are otherwise known as stacking, and the idea is that it should be sufficient for you to know how to implement one in future should you want to, but we won't consider this core content of the course. So, starting with a general overview of the motivations behind ensemble learning. Funnily enough, ensemble learning is a concept which humanity has had intuition for generations, since in essence it's a formal implementation of the idea that if you ask many people the same question and aggregate their answers, together you will probably get a better result than if you just chosen one at random. This is a heuristic otherwise known as the wisdom of the crowd. And so, this week we will extend that same approach to machine learning, taking the weak learners, decision stumps and trees discussed last week and combining them together to build predictive models which subsequently do much better on unseen data. Let's take a toy example to explain how and why this works in practice. Suppose we have a test set with 10 samples. The ground truth solution is that all should be positive. They should have class 1. Furthermore, suppose that we trained 3 independent binary classifiers, A, B and C, and each of these return 70% accuracy, but each give completely different and, importantly, uncorrelated predictions. In other words, hopefully you can see that in these examples, the zeros or wrong answers are almost never in the same place for more than one model. This means that when we subsequently combine them using an approach known as majority voting, which creates a final score equal to the most common class among the 3 models, we see that, with the exception of the case where 2 are wrong, the majority voting approach corrects all errors. This allows us to go from 3 classifiers that are wrong 30% of the time to 1 strong classifier that has 90% accuracy. On the other hand, however, if our 3 models A, B and C were highly correlated in their predictions with, in this case, completely overlapping predictions, then we see little or no improvement through majority voting. We can solidify this heuristic with probability theory, which will show that for any combination of predictions for which each of our predicted y's are correct 70% of the time, we can increase our accuracy to 78% on average. So worst case it stays the same, but sometimes we can increase as far as 100%. For this, we first need to consider 2 probability rules. First, joint probability of the 3 events. So we learned in the ICA lecture that for independent events, the joint probability is the product of the marginals. Another definition we need is that the combined probability of mutually exclusive events events which cannot occur simultaneously results from a sum. So to put this into context, you can either have a result where all three classifiers are correct, or you can have one where one is right and two is wrong, but these two events cannot occur at the same time. So in our case, we have three independent predictive models, each of which is correct 70% of the time. This leads to four different classes of mutually exclusive event for any given examples. Since either all three of our models are correct, which again, as the events are independent, has a joint probability equal to the product of the marginals, where the probability of y being correct is 70%, so this is equal to 0.7 times 0.7 times 0.7 equals 0.343. Alternatively, we can have a case where two models are correct and one is wrong. However, there are three possible combinations in which this can be true. So either the last model is wrong, or the second model is wrong, or the third model is wrong. But these events can't all happen together. So they're also mutually exclusive. So that means that we have 0.7 times 0.7 times 0.3 3 times, giving us a total probability of events occurring where two of the models are correct as 0.441. Next is the possibility that two models are wrong, which, going through the same process, returns a total probability of 0.18. And the final possibility is that all of our models are wrong. So that only has one combination, returning a probability of 0.3 times 0.3 times 0.3 equals 0.027. Then, if we combine the probabilities of all these mutually exclusive events together, we can see that it sums to 1, which is what you would expect because probabilities always sum to 1. So in this particular case, we are interested in the probability of at least two events being right, because in this case, when we combine our predictions together within our ensemble, we will return the right answer. So this means we must consider events where either two answers are right or all three are. So we know that the probability of any combination of two being right is estimated as 0.441 or 44%. Then, if we add the contribution from events where all three are correct, then this gives us a total probability of 0.784 or 78%. Note, this outcome improves further if we have more models. For example, if we instead combine 5 ensembles, this increases to 83%. A related concept for why ensembles add value relates back to the model bias and variance that Maria initially talked about in week 2. So if you remember, Maria mentioned that there are several different types of error that we face when fitting a predictive model. Bias, where high bias means that we underfit to the data by making our model too simple. Variance, where if predictions for different samples or the same sample measured multiple times varies significantly, it suggests that we're overfitting to the noise in the data. And noise or irreducible error, which relates to sources of error that we have limited or no control over. For example, measurement error, such as sources of noise in the image acquisition process that we cannot control. In total, the model error is then a combination of all these errors, which means that we can improve the predictive power of our models by reducing either bias or variance or both. So therefore, the goal of ensemble learning is to combine many uncorrelated weak learners to build one strong predictor by reducing variance and/or bias. There are several different ways of doing this. Firstly, we must consider homogeneous learners. So these combine predictions made across models all trained on the same class of machine learning method. And they include approaches such as bagging, random forests, and boosting. Homogeneous methods will be the main focus of these video lectures. The second class of approaches are heterogeneous ensembles, or stacking models. These combine predictions made from models built from different machine learning classes. For example, as shown here, for logistic regression, support vector machines, and random forests. This means that it's even possible to combine homogeneous ensemble models within a heterogeneous prediction. These methods for implementing heterogeneous ensembles are no different from the homogeneous ones, so what we cover in these lectures will give you the tools to go on and implement a stacking model. Hence, we'll only touch on these this week. Then, with respect to reducing bias and variance, there are two important subtypes of ensemble learning. These take different approaches to combining their constituent weak learning models, and it's important to know the differences between them due to the differing ways that they tackle reduction of model errors. So the first choice of approach combines weak learners trained in parallel. These, like our voting example, train separate models, ideally making them as uncorrelated as possible, and then they combine them to average away the impact of isolated errors. And thus they reduce the variance of the model. As well as voting, these include bagging models and random forests. On the other hand, sequential models train weak learners one after another, where combining them in this way enables methods to exploit the dependence between base learners such that each new learner upweights mislabeled examples. This leads to a complementary set of weak predictors that collectively reduce the bias of the model to boost accuracy. Note here, when we refer to sequential models, we essentially mean the class of methods known as boosting. These include several different approaches, including adder boost, gentle boost, and gradient boosted trees. We will see that as well as reducing bias, these methods have been shown to be robust to overfitting, and thus they also reduce model variance. So in summary, ensemble learning methods improve prediction accuracy by combining the predictions made from many different learning models. They can either combine predictions made on methods of the same class, where they're known as homogeneous ensembles, or from different classes, where they're known as heterogeneous ensembles or stacking models. They can also take the approach of either combining models trained in parallel and combined at the end. This has the impact of averaging away isolated errors and in this way reducing model variance. Or ensembles can take the approach of training models one after the other in serial, upweighting misclassified examples each time in order to improve the performance of the prediction on difficult to predict edge cases, in this way reducing bias and at the same time decreasing variance. In the next video lecture we will go on to look at parallel methods, bagging and random forests in more detail, but before going on to do that, please complete the Keats quiz on this section.